All right, so let's get started then. I think everybody's online. A couple of people said that they can hear me online. One person said they couldn't. If you can't hear me, then given that other people can hear me, I guess check your local audio. This is, now we've moved in. We were working with just simulation, and now we're going to focus a little bit more on discrete event system simulation, which will get closer to the things you've seen in your homework. In the thing that so already in your homework, you've talked about just generic modeling, but now we're going to actually go into the timing of a real discrete event system simulation. So where are we? So there's an ICA that's coming up before Thursday. So that ICA is available. So so I think there are 12 ICAs this semester, and you can drop something like 7 of them or something like that. Double check on Canvas. So these are opportunities. These are not requirements. So don't view them as if you don't really have time to do them that week. That's fine. There's plenty of opportunities to drop, but if you do have time, it's meant to sort of help shore up some of these ideas as we go along. So that ICA is due before the next lecture, Thursday's lecture. Lab 2 is this week. So Lab 1 was kind of just basic, we start getting into what are entities, et cetera, and what are some simulation platforms. In Lab 2, there's going to be a hand simulation assignment that's actually similar to the kind of second question on homework, the homework B1. So because of that, you'll see some overlap between Lab 2 and homework B1, and some of the assistance that's provided for one might help you on another and vice versa. So with that also, homework B1 is available to do in approximately 1 week, upload to Canvas, cover some simulation basics. And again, there's also that a hand simulation, and we're gonna kind of get into how to do hand simulation in this lecture, and then getting into more detail in Thursday's lecture. So that's kind of the roadmap so far. Couple other side things here. IISc and Rockwell. So by the way, there is an IISc student group working on getting some information on the Canvas site about the IISc student group. If you're not a member, encourage you to join. A lot of benefits from starting that community early in your career. And then there's some dividends that pay off later in your career as well. That group, along with Rockwell, sponsors an arena competition every semester where up to 3 undergraduate students get on a team. And after you enter, you're then given a prompt where they'll give you some data and a complicated kind of simulation problem similar to what you might see in the real world. And you're asked to put together an arena-based simulation. There are cash prizes for first, second, and third. All the finalists get flown to, at least normally, I'm not sure if they're necessarily doing it exactly this way this time, but normally in normal years, all the finalists get flown to a major conference where they get to present their simulation models, and then then they end up getting sorted into the first, second, and third there. So that is an option that if you would like to pursue this, you can use this as your final project for this class. Occasionally we get a couple of people who enter. They're definitely love to see though the ASU participation in this contest. You don't have to do this, but it is an option. So I'm just putting that out there. If you want more information, you can find it on the website, on the Canvas site, linked from here. So the deadline to enter is at the end of September. I think it's September 30th. So yeah, so that's an option for your final project that I'll remind you of for the next couple of lectures. Other things, some of you have started to install Arena. The Arena 16.1, it's not been out that long, so I'm not familiar with all of the potential installation problems. I have seen at least one student since I've been working with Arena 16.1, and I've never had this problem myself, but get like a partial installation, and then if they try to reinstall Arena after a failed installation, it says it's already installed. And in that case, they can go into add or remove programs, find it there, even if it's not in the start menu anywhere, remove it from there and then reinstall, then usually things go fine. If there are weird other issues with 16.1, we'll work through them, but I don't know of any except for, again, this weird partial installation thing where you have to remove it from add remove program. So if you don't need Arena yet, and because that won't be until Lab 5, and even if you can't get it installed in your local machine, you can always access it via remote access on the SIDSI virtual lab. It's installed there and working. So that's an option for everybody that you can use. Of course, you can also use it live on the real SIDSI labs too. The other things, that there are other competitions that I'm also happy for you using for your final project. that also have, they're sort of opening now and have registration deadlines coming up. So Flexsim is a competitor to Arena. And so IISC with the Flexsim team also sponsors a very similar competition, but this discrete event system simulation competition is focused on healthcare. And so if you're interested in healthcare systems, they'll actually accept teams of up to 4 students, and the 4 students can even include a graduate student or 2. And so if you're interested in that, it's kind of a similar thing. They've got cash prizes for 1st, 2nd, and 3rd place. It's, like I said, administered by IISC, so Bonnie Cameron is also the person you can direct questions to. So feel free to use this as your final project instead. I know it's not Arena. We can't give you Flexsim support because the class is built around Arena, but all of the fundamentals, you know, entities, resources, et cetera, are all the same in Flexsim. And then if you find any other simulation competitions out there, for example, Simeo, the people who built Arena left Rockwell years ago and started their own company to rebuild a simulation platform they call Simeo that's meant to kind of be like an Arena 2.0. And so it shares a lot of the kind of intellectual motivations behind Arena, and a lot of companies use Simeo. They have their own annual competition as well, and I'm willing to consider these for the final project too. So if you want to do any of these competitions, just let me know, and we can talk about whether you can use those as your final project. In most cases, as long as it's discrete event system simulation, I'll be fine with that. All right, so any questions about administrative stuff? I see some questions in the chat. If we enter a competition to use for our final, does it have to be a team of students in this class? That's an interesting question. So your final project must be with a team of students from this class. Now, you could, I guess, conceivably enter into a competition with students outside the class, but you'd want to make sure that what you'd submit for your deliverable for this class would somehow be distinct. So I don't want it to be an avenue for people who've already taken this class to sort of help you with your final project. So it's going to be easier all around for academic integrity if you limit your teams to people in this class, but it's not impossible to have created a competition team with students outside this class. You just have to be more careful about what you submit to this class in terms of deliverables only being a function of people in this class. And you still want to make sure that that you might end up participating on one team and you being the overlap with a group in this class. So there could be like, there's 4 students in this class and 2 of you are on the competition team. So you've got another 2 students outside the class who are on your competition team, but you end up kind of working on 2 projects in parallel that just have a little bit of a shared, you know, maybe model on that. So I prefer not to get into that sort of mess, but if that's something that really works well for you, then we can talk about it on a case-by-case basis. All right, any other questions? I don't see any on the online. Anything in the class? Okay. Great, all right. So from last time, where we kind of left off is that we defined discrete event system simulation, discrete event systems, where the discrete part of discrete event systems is that these are systems where the system changes its state only at countable instants of time. And so there are instants that pop up where where the system moves from one state to another. And those are events. We call those events. And so someone just entered the class. So the instant the door opened and that person walked into the class, that is an event. The state is the number of people in the class. And so at that instant of time the door opened, then the state of the system changed by 1. It went up by 1. Now, how much it goes up, that doesn't have to be countable, but the instant of time, so you can say at 10:35, at 10:47, those are countable instants where the state changes. That's what we mean by discrete event. And systems are viewed from a process-centric perspective. And so what we mean by that is that we model all of the entities individually, but we don't give the entities agency. So students in a classroom model are passive students. So in the real world, of course, students make their own decisions, et cetera, but we model them as being these marbles that are controlled um, by some other process here, like this little box here on the left that creates them and then holds on to them for a certain amount of time and then injects them into the other processes based on availability and timing. And so we don't model the students, the entities, as making their own decisions, but we model them as kind of being born forth and then being moved around based on timing, which is set by the process. And so it is a process-centric. We view things emerging out of the external process and not from the entities themselves. That's what we mean by a process-centric approach. All right, so are there questions about that? Mainly like this part here about discrete events. That's kind of the big thing here. Does everybody understand what I mean by a discrete event? All right. Okay, entities are focal objects that flow around the simulation. So we already kind of talked about this. Like I said, they're passive. They get created, move around, and can leave. These are usually equivalent to real tangible things like real students in the classroom. They don't have to be. So I'll give you an example coming up where we kind of move around, we kind of change the relationship between resource and entity. There are a bunch of other more advanced examples that you'll see later on in the class as you work through labs, where you can have these sort of fake entities. Like for example, if you're modeling a traffic light changing from green, changing the cycle, so north-south getting the green, and then east-west getting the green, going back and forth. You can have an entity that sits inside a loop where it's a single entity that is constantly being delayed for whatever the cycle time is. And then after that delay, it cycles back around to the front of that delay and meanwhile toggles the state of the traffic light. And so that's an example where this entity is constantly being recycled in the system. And every time it recycles, it switches the state of the traffic light. And so this isn't a real entity in the real world, but it is convenient for us to model an entity in doing that toggle back and forth. So sometimes we have to think about virtual entities when we build these models. And but for the most part, these will be real things that are flowing around real systems. Each one of those entities can be discriminated from itself by its attributes. And so we want to differentiate between entities. You can have a bunch of students, but some students, maybe have a different course schedule than other students, that sort of thing. And so we might want the process to treat them differently. Again, because this is a process-centric perspective, any differences in how entities move around have to come from the process, which means if we want some entities to be treated slightly different than other entities, they have to be very conspicuous about their differences. And that is what we use the attributes for. We label them as this entity has already been scanned, so treat them differently than the other entity that has not been scanned yet. So common types of attributes: arrival time, due date, priority, color. We'll see a lot of these sorts of things. These are local to each entity. They follow the entities around. When the entities leave, they disappear. They can be changed during a simulation. Entity can enter the simulation having not been scanned yet, but then once it's scanned through as part of the simulation, its attribute changes, and it might then be treated differently later on in the simulation because it's been scanned and other entities have not. So attributes can be dynamic, but the key feature to them is that they ride around with the entities. This room can have a state variable associated with it, whether its lights are on or the lights are off, but each one of you can have an attribute associated with you, whether you're awake or asleep, for example. And so those, as an entity leaves, we lose that information. But the state of the room, that global state variable, is always with the room. The room is the resource. So we can have global variables, but these attributes are kind of the local variables that follow each entity around, so we can treat each entity differently with the same process. Any questions about these distinctions? Entities, attributes versus kind of global variables. Okay. Questions online? Okay. All right. Resources. This is like a key feature of discrete event system simulation is that we have resources. This is the big part of the process-centric perspective is that entities compete for resources. And so the only reason that entities get slowed down is because they need access to a resource and that resource is not available. Usually it's not available because another entity is using it. And so we have competition for these resources. So because of that, sometimes it's actually useful in your modeling to not think of the entities first, but think of the resources first. You could say, what are the things that are really the bottlenecks in my system? What are the things that are slowing down my system that are preventing it from traveling at light speed? And once you identify those, then you could say, oh, the classroom is an example of that. Like, say, well, okay, well then what is the classroom delay? From then, you can say, okay, the classroom is preventing students from entering the classroom because they have to wait for the previous class to be over. So you can say, aha, so the classroom is a resource, the activity is the duration of the class, and those being delayed are the students trying to enter the class. So the students must be the entities. So sometimes it's easier to start with the resources and then figure out from there what are the activities and what are the entities. So like I mentioned, people can be resources, equipment, space, etc. An entity, we often say, will seize a resource and then release it. So if you're going up to a cashier, a clerk in a store, you temporarily have sole access to that cashier. You seize that cashier. That cashier belongs to you for the short period of time you're with that cashier. Once the cashier is done with you, you release that cashier and the cashier becomes available for the next person. So that's what we mean by seizing and releasing. Seizing and releasing are usually events that arrive to the cashier. That is an event that kicks off seizing the cashier. The activity of checking out your groceries, that activity, when it ends, that triggers an event, which then generates releasing that resource. And then that, during that activity period, the resource is sort of temporarily assigned to the entity. Yeah.
Is there a way to model like multicast abilities? I've been to QC and that guy kind of was pretty quick with multiple categories. Is it possible like resource take more than one entity at a time?
Absolutely, yes. So this is kind of a simple model where you get one entity for one resource, but you definitely can say that this resource, you can have capacities of resources, for example, and so you can say that this resource can handle up to 2 entities before it starts blocking others. So that's one thing that you can do. There's all sorts of interesting things we can do also with resources. We can say that this resource can handle entities of type A, B, and C. This resource can handle entities of type C, D, and E, and they both overlap in C. So you can implement some interesting kind of cross-training type of situations, and then we can actually allocate entities to resource sets. So instead of saying, go seize a resource, you can say, go seize a resource from set C, and it will seize whatever resource is available, either it's the ABC or the CDE resource. So there's all sorts of interesting things that we can do inside the model that help us model things like cross-training, multitasking, et cetera. And those are more advanced, but you'll see those once we start working with Arena in lab. Other questions? Questions online? And this is kind of, that was a nice, dovetails into what I was saying here. Resource can have several units of capacity. So I'm gonna, usually for simplicity, I'll often give examples where there's a single resource, but we can think of a resource, a classroom. We can think of seats in the classroom, and this classroom maybe has 80 seats. And so there's a resource capacity of 80. 80 students can enter this classroom, and once 80 enter the classroom, once it's been seized 80 times, then no one else can enter. And so that's what we mean by capacity. How many entities can be using the resource simultaneously? That's the resource capacity. And when we define utilization, we'll often define utilization in terms of how many units are being used divided by how many units total. So if this was a 50% utilization, that would mean that 40 out of the 80 seats would be taken. Okay. Questions about that? Pretty clear? Questions online? All right. So I want to sort of change our reference frame just a little bit. I've talked about examples so far where entities are the things that are moving and the resources are stationary. But we can flip that around. And so modeling a vacuum cleaner, an autonomous vacuum cleaner, is a great way that we can do this. The vacuum cleaner is actually the limited resource. And so there's only one vacuum cleaner, and every vacuuming session, there's always a vacuum cleaner in the vacuuming session at the beginning, at the end, it never leaves. The vacuum cleaner is moving around. What arrives and departs are the dirt that the vacuum cleaner encounters. So with that in mind here, I can think about the vacuum cleaner moving around a space, encountering random bits of dirt at different spots, maybe even different types of dirt. And if I were to think of myself riding along on the reference frame of the vacuum cleaner, then from this perspective, the room is moving, not the vacuum cleaner. So from this reference frame, this resource becomes stationary, but dirt is flowing in to the vacuum cleaner. So that dirt becomes the entity that comes in and then maybe is disposed as it gets collected inside the vacuum cleaner. So in this particular case, even though in the real world, the vacuum cleaner is moving, we might model the logic going on the vacuum cleaner. Do I linger in this area? Do I pick up this type of dirt? Do I pick up this other type of dirt, et cetera? Those sorts of decisions might be modeled in the model as if the vacuum cleaner is stationary and the dirt is just arriving to the front door of the vacuum cleaner. And that perspective is one that in my own research, we've taken when we model, for example, undersea exploration vehicles. So the vehicle is moving around the ocean and it randomly hits things that it might want to loiter around to do more investigation of. We model that as if the ocean is moving around the vehicle and these opportunities are just arriving to the vehicle, just like students arriving to a classroom. Similarly, autonomous air drone, it's the same sort of thing. Even though in the real world, it's the one moving around, we can model it as if it's stationary and the world is coming to it and it has to make decisions as things are encountered with it. Flexible manufacturing systems, conveyor belts and so on, another sort of thing where maybe the resources are moving, but in the real world, but in our model, we model the world as being moving around the fixed resource. And then when ecologists do this, they use discrete event system simulation models, and they model, say, for example, predators as the kind of resource, and the entities are the prey that they're hunting down. Now, in the real world, the predator is moving around to find the prey, but in the model, we might model the predator as a fixed resource, and there are arrivals as if the prey are just coming to the predator, and then the predator has to decide, do I eat this prey or do I wait for the next one? But it's as if the predator just has to sit there and wait to ambush these things, even though in reality, the predator might be moving around. So I don't want you to build the heuristic that entities have to be moving and resources have to be fixed. That's not the kind of idea here. What we mean by resources being fixed is really that resources are always in the system at the beginning of the sim and at the end of the sim. They're the thing that's limiting, that's preventing the system from running at light speed. And entities are the things that are ephemeral. They're sometimes there, they're sometimes not. In the real world, what's moving or not is kind of irrelevant. It's just whether things arrive and depart, and how they get there, that's going to depend. Does that make sense? Are there questions about that? Okay. All right, so the other couple of definitions that we needed from last time, state variables. So I already mentioned state. At every event, the system moves from one state to another. We keep track of those states in state variables. So whereas there might be 30 people in a class, and when somebody arrives, there's now 31. Well, those are two states of the system, 30 and 31. Both of those are stored in a state variable X, or number of students in the classroom. So the state variable is the actual thing that we use in our symbolic notation when we write formulas, whereas the state is actually the numbers that those variables take on. So T might be a state variable, whereas 78 degrees might be the actual state. And so these are these variables, every one of them might be updated every step of the simulation. The steps of the simulation are those discrete events. So like I said, queue length may increase or decrease on every arrival or every cashier completion, et cetera. And we can respond dynamically to these things. So you can actually say before your simulation logic can depend upon the state. So you can say, if there are 50 people in the queue, then normally I would have an arrival rate of 1 per second, but I'm going to simulate bulking. And whenever there are 50 people in the queue, people stop arriving because they see the 50 people and they go the other way. So I can make my arrival rate change based on the queue length if the queue length meets certain criteria, and that's how I model certain things like bulking. So any questions about that? The idea, the distinction between state variables and state, and how we use state to build logic. This will become more concrete as we start doing examples, including the kind of hand simulation. Any questions online? I don't see. Okay. Activities versus delays. Like I said, activity is a duration that is known before the simulation. We can sit with a stopwatch next to somebody doing a document check. And so if a document checker is sitting there and people are coming up to the document checker, then we can then, with a stopwatch, say on average, the person takes 30 seconds to check a document. It has some distribution. It goes from 15 seconds to 45 seconds, and maybe model that as a triangular distribution. But we know that ahead of time before even running the simulation. What we don't know from the simulation is how long people wait for the document checker. So that's the distinction here between the activity and the delay, is that we can know ahead of time before running the sim the statistics of document checking. But if you were to ask me, how long is someone going to wait? Then you say there's all these conditions. Well, if there's nobody in front of them, they don't wait at all. If there's 100 people in front of them, they wait with a distribution that looks like an Erlang 100. So we have to figure out what that distribution is. If there's 50 people in front of them, if there's 500 people in front of them, all of that wait time depends upon the state of the system. So delays are things that depend upon the state of the simulation. And if we can't fix the state of that simulation as being constant, so if it's constantly changing because it's dynamic, then the only way we're going to be able to really measure delay is by running the simulation. So a delay is an output that is measured after or during a simulation run, whereas an activity is an input that we use to characterize activities within the simulation. Is there questions about that distinction, about activity versus delay? This is like super important for discrete event system simulation, the difference between our inputs and our outputs. And just reviewing the stuff that we introduced last time. Yeah. So there's a question of, can delays and activities be the same? Well, they're actually a different category. So it's to your point. So I guess you could say that you could ask an entity, how long did you wait getting through the whole system? How long were you work in progress? And in that case, if one person arrives to the airport and they don't have to wait on anything, then it's true that their wait time might just be a sum of all the activities, in which case there'd be no difference between, in that case, I would say there'd be actually no delay. So the delay is the slippage, or is the slop between the activity and the total time. So that's the way does that answer your question? Yeah. Any other questions? Questions online? All right. All right, activities, I do want to just sort of stress, activities may be variable, but their statistics, mean, standard deviation, do not depend on the system state. So I don't know the exact time a document checker takes to check a document. I know a distribution of times, but that distribution does not depend upon the system state, whereas a delay for an entity is an accumulation of activities experienced by other entities. So that's something that I don't know how many other entities are in the system or what the particular activities are for each one of those other entities. So the delays, I just cannot really know ahead of time. So that's kind of the big thing, is that I know it ahead of time, it's an activity. I'm saying for certain in this system, I am going to assume that these activities do not vary with the state of the system. Then that means I am calling them activities. Whereas other things I'm going to model as things I don't know, and I'm running the simulation to find out. Okay. All right, any questions about our terminology there? We're going to be using these terms just over and over again throughout the semester. Activities, delays, entities, resources, etc. These are the terms you'll see that'll pop up in the software programs as well, and are the common terms we use to talk about these systems. Okay. Now, I mentioned last time that our discrete event system simulation tools are stochastic modeling tools. And the basic idea there is that if we think about, say, arrivals to an airport, there is a lot of variation in how long you wait between arrivals. And we, rather than trying to model all of the deterministic details that cause some people to arrive at certain inter-arrivals than others, then we replace that with randomness. And we sort of say, well, what if we just randomly drew these inter-arrival times between all of these customers? Now, by itself, not any random variation is going to work. We need to craft the random variation to make it realistic. The same way when you play a board game, there's a certain schedule for as you roll the die, certain outcomes occur more often than others. So if you roll a 2 through a 6, this outcome occurs, but if you roll that 1, this other rare outcome occurs. Well, somebody had to decide, well, that, how rare is the rare event? Well, in that case, it's pretty rare. But if it's an even thing, you'd say, well, run a 1 through a 3, you win. A 4 through a 6, you lose. Well, in that case, it's a half and half. So in a board game, you can decide on different schedules that you assign to the different die rolls. We have to do the same thing when we do this. We do our simulations here. Our computer is going to generate a random number, which may as well be a die roll. And we inside Arena are going to say, when that number comes up in certain intervals, we're going to get certain outcomes. And if we do that mapping just right, then our random outcomes here will look realistic. So that is stochastic modeling. It is replacing something from the real world that may or may not be random with randomness, because it's easier to model with randomness, because a random distribution is only going to have 1, 2, 3 parameters we have to worry about. Whereas the deterministic details of what goes into this variation in real life, that might have hundreds of parameters. And if we parameterize it for one system, it may be totally different for another system. So hopefully by using fewer parameters, we get more generalizability and generally make the modeling a lot easier. So that's the idea between stochastic simulation, few parameters in our distributions. The challenge here is that every time we run our simulation, we're going to get different results. So now our simulation gains the stochasticity that we have put into it. So it in itself becomes an experiment that we have to run multiple simulation runs. So if we happen to show that our operational strategy is better in one simulation run, we can't trust that. We might have to run 10 simulation runs and say, look, 7 out of those 10 runs, our new strategy was better. So we then need statistical methods to say that that's enough, 7 out of 10, for us to then infer that that on average, our new operational strategy is better than the baseline. So, but we now need to use statistical methods to deal with the fact that our replications are random. So, so that's something that we introduce, a challenge we introduce when we do stochastic modeling. All right, questions about that? Is that clear what I mean by stochastic modeling and how stochastic is slightly different from random? Randomness is just probability. Stochastic modeling is a stance that we are going to model a system with randomness to make it easier, because we think that that's, even if the real system is not random, we're going to model it as if it's random because it just makes it easier for us to do the modeling and to get the generalizability. Yeah.
It kind of sounds like one stochastic simulation doesn't really do a lot for anything. It's like the multiple runs, the overall view, the big picture of it that kind of actually benefits anybody.
Right. So that's a good question. So the question is how many. So the question here was, it seems like one simulation run of a stochastic simulation isn't very meaningful because you end up having to run because of this variability. You could have just gotten lucky at the end of the simulation. If I understand what you're saying. And in some ways, it depends a little bit on the variability. And it also depends on, we have ways to run very long simulations that that have so many customers that if we're looking at a customer specific performance variable like waiting time, then a single simulation under some cases actually could be multiple replications because you have millions of customers. But in general, the basic question of how many replications, how many customers I need to simulate has to do with how variable things are. So if the real system in the real world has a lot of variability, then my simulated system that represents the real world is going to have a lot of variability. And if I'm going to need to demonstrate that my new system is better than the baseline system, I'm probably going to need to run a lot of replications because most of the performance difference between my baseline system and my hypothetical system could be accounted to just because they're both extremely variable. But if I run the simulation and every time I run it, it comes out with 4 is the answer. And then I run my my hypothetical simulation and it comes out as 5 almost every time. Then in that case, maybe I only need 2 simulation runs of both because there's just not a lot of variability. So this is the notion of statistical power that we will get into after the midterm, which goes into figuring out, based on how variable the system is, how many replications do we need of a simulation run? But we almost always need more than one. All right, any other questions, online or otherwise? All right. Okay, so I'm using this term. I don't think I introduced it here yet. I mentioned that we input variation. So we purposely introduce randomness, variation. So distributions for every process, distributions for inter-arrival times. We input variation. That variation gets shaped by the flow chart that is our process and our process-centric perspectives. So the inputs are the activities, and then the output are the delays. And so the variation we put in gets squeezed through a sieve, and then it comes out looking slightly different, but it's still variable. And then that variation we then study with statistics. So the inputs to our systems are not the entities. The inputs to our systems are the variation that we put into the the activities, for example. So these distributions that we use, these probabilistic distributions, those are the inputs. So we have to make sure that our inputs are realistic. So when we talk about the duration of time it takes for a document checker to check documents, if we put in a fictitious document checker that takes 2 seconds to check a document every time, no variations, always 2 seconds, we might get a simulation with beautiful results. So the simulation, that's the structure in here. So if we put in that document checker, and that document checker has got this, he just flies through checking documents, then the output, so people's waiting time in getting to their flight might look beautiful, and it might be variable. It might look, maybe it's realistic, but in the end, a real document checker probably doesn't take exactly 2 seconds to check a document. Maybe sometimes it takes 2 seconds, but other times it takes 20 seconds. So we need to make sure we come up with realistic input models, because the same process may end up giving us very different results if we choose the wrong input models. And I draw this analogy with fashion. Regardless of how attractive you think the fashion models might be, your goal is to evaluate the fashion, not the models. And so if you push attractive models into bad fashion, sometimes you can get an okay looking result that convinces you to buy that fashion. But in the end, you're more focused on the models and less on the fashion. So that's why we might want realistic fashion models, people that look maybe like you. They have your skin color, your build, your hair type, etc. Because then they give you a more realistic view of the fashion or a more realistic view of the process. So that's kind of what I'm trying to say here, is that insightful outputs require good inputs. And so the role here is for us to choose insightful, good inputs, good probabilistic distributions to go into these models. And then the variable outputs require replication and statistics. And so we can't just run once. Even if we get a good result on one simulation run, we might need to run 10 simulation runs to really be able to be confident that our result is good. So, so the big term here that I want to introduce is input modeling. That is a term that we're going to be using throughout the semester. Input modeling is this idea of coming up with the probabilistic distributions for these inputs. So what is a good model of a document checker? Is an exponential distribution a good model of a document checker? So we have two types of models. We have a model of the system. We also have a model of the activities within the system. So before we can run our system model, we have to build probabilistic models of the small scale activities within the system itself. And that's what we refer to as input modeling. The inputs are the probabilistic distributions, not the entities. The entities are just part of the system. All right. So any questions about that from online or otherwise? I'll put up the little question slide here. Anybody? Does that seem pretty clear? Those are kind of the terms and everything I want you to be up to this point before we introduce new stuff for today. All right. All right, well, let's do a quick attendance question. And I guess my my question here, so you can either go to the URL, which I can try to type in the chat for those online. And then, or you can go to the QR code, type that in. The question I have for you here for this attendance question, which is your answer to question 1, is what are the inputs to discrete event system simulation models? So what are the inputs to the models? What do we mean when we talk about inputs in our case here? I told you that they're not something, but instead there's something else. So what are the inputs? And you can, you know, as long as I kind of see where you're going, when I scan through these, you're fine. If it's a 2-word answer, that's fine. All right. Let me focus back on here. Try to focus back on here. There we go. All right, so I've talked a lot about discrete events and time and activities and durations. So how exactly are we going to formally model time in these systems? What's going on behind the scenes now it moves from event to event to event? So we are going to take in discrete event system simulation what we refer to as an event scheduling worldview. There are a bunch of different worldviews. You can say, how does time move in a simulated universe? In a simulated universe, time could move where everything is a tick of a clock, where everything is separated by exactly a certain amount of time. So a lot of times when people think of simulation, before they take a class in DES, they think of simulated time that way, that every microsecond we move ahead, see how the world's changed. And then the next microsecond we move ahead, see how the world's changed, and so on. That is not how time flows in discrete event systems. In discrete event systems, we focus on events where we jump in irregular steps from event to event to event. So events are points in time where the state of the system changes, and we're going to jump from event to event. We're going to jump in irregular jumps. So it might be like in this classroom, a bunch of people arrive all around 10:30, and then maybe somebody arrives at 10:37, and then nobody arrives after that. So from the event scheduling point of view, we get our clock move every time somebody comes to the room, the clock moves ahead for every person that arrives at the room. And then it pauses for a while until it jumps ahead to 10:37, where that last person arrives in the room. And then after that, it doesn't go anywhere until the end of the class when everybody leaves the room, if all we're modeling is the occupancy of the room. So another worldview might be to model how many people are in the class every minute. And then at that time, you get a time series where every point would be a minute separated. That is not the time series that's generated from these systems. In these systems, you get a bunch of activity early, and then it would just sit flat. And then the next event, which would be the next thing you immediately jump to, is maybe at the end of class where people start going out of the room. So we don't care about things in between the events. The only time the clock will ever move is when some part of the state changes. In other worldviews, the clock moves even though the state doesn't change. So the simulation iterates through the event calendar. In Arena, there is an event calendar that can actually show you all of the events as it's moving through them. You don't generally need that as a designer, as a programmer, but if you're debugging your program, sometimes it's useful to look at that event calendar. So at each event, the simulation clock is moved to the time of that event. Certain logic, like an arrival happened. Well, certain things have to happen to deal with an arrival, is going to be executed. And then this is the kind of the nuance to make this thing work. After that event is processed, we need to then schedule future events on the calendar. So if we were in a worldview where every time we step a minute, we step a minute, we step a minute, we always know how the clock moves. Here, we actually have to tell the clock what the next events are going to be. So we are going to, the simulation Arena is going to be managing this event calendar, this clock jumping schedule. And every time we execute an event, that may schedule new events. So when someone arrives, then we might want to schedule their departure. So we know that someone needs to leave class early because they have a doctor's appointment. Well, then when they arrive, we process that event, but then we schedule on the event calendar when they're going to depart for that doctor's appointment. So we know on average, they're going to stay in the class instead of 75 minutes, maybe 60 minutes. So we draw a random variable with mean 60 minutes, and then we take that duration and we schedule that as when that student leaves a little bit early. So we need to schedule all of our events, and the clock, instead of stepping in lockstep, 1 minute, 1 minute, 1 minute, it follows the event calendar. So we're constantly updating the event calendar and stepping through it. So that'll become more concrete as we do that. Right, so the event calendar is basically an ordered list of events. It will also be called an event list or a future event list or a schedule, depending on which textbook or which software program you're looking at. The computer scientists refer to this as a priority queue. So most queues are first in, first out. A priority queue is one where the item that is taken out is the one that has the highest priority. In this case, temporal priority, it's the earliest event. So you add events with some time, and then they then are inserted in the right order so that the next event that's taken off the queue is always the earliest event. So that's what we call it, a priority queue. So the two fundamental operations, remove the first item and insert a new item in order. So that's what we mean when we're scheduling a new event. You have access to the event calendar as a programmer, but your simulation does not. You cannot build simulation logic that looks at the event calendar. You as a debugger can look at the event calendar to see what's coming up, to see if maybe there might be something wrong in your logic, but the logic you write cannot reference the event calendar. You cannot look ahead and say, how many events are in the future? Based on that, I'm going to change how my system works. Because the event calendar is not a real thing. This is an abstract thing just to keep simulated time moving. It is not something that actually exists at a real airport, at a real grocery store, etc. So hopefully that'll become more clear as I step through this. Are there any questions about this basic idea of the event calendar so far? You know, it might help as I work through this next example.
Is it more like an event log versus an event calendar?
I view it as that's a great question. So the question was, is it more like an event log than an event calendar? It's like a future log. So once things are processed in the event calendar, they're removed. And so the event calendar tells you what things will come up in the short-term future. not the long-term future, because as you process events, they schedule more events. So it's like the inverse or the complement of a log. It doesn't keep track of what you've done, it keeps track of what you know you definitely will do, but not necessarily everything you will do because you haven't maybe scheduled everything yet. So it's like view it as a calendar or a schedule. It's what's coming up. Okay. So as an example of that, let's say we're modeling a simple system here where we've got cars coming to a car wash. Let me make sure there's no questions online. Okay, so cars enter a car wash. The cars are entities. They arrive and depart. They're ephemeral. They come and go. The car wash and the vacuuming station, those are the resources that are always there that the cars are competing for. So there is some sequence of events that will occur when we run this simulation or when we describe the real world event or the real world car wash. So we can see these events here, and these will disappear in a second as I start simulating this system. But at the end of the simulation, if you kept track of everything that happened, you would have a log like this, where a car arrives, it enters the wash, another car arrives, the other car is ready for the wash, but it can't enter the wash because the first car is in the wash. The first car leaves the wash and enters the vacuum. At that point, the second car can enter the wash. And so eventually then the second car exits the wash. So these are all events that occur that change the state of the system. The car enters the wash. Well, the state of the car wash goes from idle to busy at that point. So these are all the state change times in the system. Now, when we start our simulation, we don't know any of that. So how do we build that simulation? How do we simulate this world? Well, the first thing we do is we start at the first arrival. That's usually where we start a simulation. We look at our entities, and there's always some entity that arrives at time 0. And we say that, okay, car A is going to arrive at time 0. We're just going to jump to time 0 being that time when the first car arrives. Now we have to think about what happens when that first car arrives. And we're going to gradually add things to the schedule based on what we know when that first car arrives. So one thing we know when the first car arrives is it's going to take time for that car to drive from the entrance to the car wash to the car wash itself. So that takes a certain amount of time. On average, it's 5 seconds. Sometimes it's 4, sometimes it's 6. So we draw a random number that is of some distribution, which represents the time it takes to drive from the entrance to the facility to the actual car wash. So that's going to cause us to schedule an event where car A enters the wash. Because we know that the wash is currently idle, then we know that it's going to drive there and enter it. And that's why I'm going to schedule that it enters the wash. So that's what I mean by scheduling. What do we know when car A arrives? We know that a little bit later, car A will hit the car wash. Now, what else do we know? Well, whenever I process an arrival, I know there's going to eventually be another arrival. Well, another activity we have are the inter-arrival times. And so you've gone out there and you said, I know that people arrive to this car wash around the 2 p.m. hour, about 3 every hour or something like that, or maybe 30 every hour, whatever it is. Well, you could figure out on average, how much long do you normally have to wait between one arrival and the next arrival? Whenever you process an arrival, you must schedule the next arrival, or else arrivals will cease to happen. So that would be a bug in the system. So we know that before we can let go of the car A arrival, we draw from a random number generator to find out what is the duration of time between the car A arrival and the car B arrival. On average, it's 20 seconds or whatever. This particular time, it came up 17 seconds. So we schedule 17 seconds in the future, the car B arrival. So we know those things are going to happen in the future. That's why they're on the calendar. They're in the schedule. At that point, we're done with the arrival processing, and we jump to the next thing in the calendar. It just happens to be something we just scheduled, but it doesn't have to be. It's just the next thing in the priority queue. And so we know the next thing that we're going to process is the car A entering the wash. This is a different type of event. So at this point, we have to say what happens when cars enter the wash. And we have to then schedule things based on that. Well, we know the wash takes a particular time. It takes a certain duration. Washes take on average a minute. Sometimes they take 59 seconds. Sometimes they take a minute and 5 seconds. They take on average a minute. So I'm going to draw from a random number distribution that has the right statistics. and that'll give me my duration. That'll say that in the future, I know eventually the car will exit the wash based on that duration there. So that's all I have to do when car is enter the wash. That's the last piece of logic. And so I let the simulation go to the next thing in the calendar. The next thing in the calendar is now a new arrival, a car B arrival. And now I run through the same process logic I did when car A arrived. But the state of the system has changed because now car A is in the wash. So car B arrives. Oh, I think I jumped ahead a little bit here. I know that I have to schedule it to go to drive to the car wash. But because the car wash is currently busy, the event that I'm scheduling in the future is not car B entering the wash. It's that car B is at the wash. It's ready for the wash. And so I schedule that thing in the head and I jump to that. And now I have to say, well, what happens when car B, ready for the wash, can't get in the wash when car A is still in there. So this is an example of where we have a delay. So by running the simulation, because the A and B arrivals weren't quite lined up perfectly, there's a time that B has to wait for the car wash to become available. So what I do now is I'm going to add B to a queue, a state variable inside my simulation that represents how many cars are waiting for the wash. So there's a state variable inside here that just is the line of cars waiting for the wash. And the amount of time that it's going to wait is again part of this delay. And we don't know this until we ran the simulation and we revealed this delay. So we jump to where the car A exits the wash. At that point, the car B that's been waiting can now enter the wash. So we're going to empty the queue and schedule when car B is going to exit the wash itself. So we're going to schedule when car A goes to the vacuum. We are going to empty the queue so car B can now enter the wash. And now, because car B's entered the wash, we're going to schedule when car B exits the wash and go forward and forward on and so on. And so that's the way behind the scenes Arena will be generating time steps, is that at every event, it's going to say what events can I schedule into the future. And after I've run through all the process logic for an event, then I ask, what's the next event on the calendar? And that's the next event it processes, and it starts the process all over again, and so on and so forth. So are there questions about that? This general idea that I could start from an empty calendar and an arrival at time 0. And in theory, if I know the probabilistic distributions of activities, I can go through and schedule all the rest of these events and just crawl along that. Does that make sense? And that's what you're going to start doing by hand in the lab 2, as well as homework B1. But then after lab 2 and homework B1, then software is going to do all of this for you. But you have to know this is going on behind the scenes, because sometimes you have to debug this stuff. And so you need to go and look at the event calendar and see, why are things not quite executing like you saw? And sometimes that shows that, oh, I forgot to do this particular thing. I forgot to, I don't have the right activity durations, and that's why these are being scheduled in the wrong order, et cetera. So we have to know this is going on behind the scenes, but you're not going to manually do this after these first 2 assignments, homework B1 and lab 2. So questions about that? Does this seem roughly clear, or at least not quite so muddy as it could be? Okay, so we generate this whole list. So like I was kind of hinting here, inter-arrival times and service times, these are activity durations. In the first homework and lab, we're going to provide these to you deterministically, as if they were known like hard numbers. After that, though, we're going to learn that they can be drawn from random distributions with given parameters. So instead of saying, what's the next activity in the list, I'll say, draw another random number from a normal distribution with this mean and this standard deviation. So that's where we're going. But to get there, to make things simpler, then I'm going to give you the activity durations and the service durations explicitly in a list, in the first homework and the first lab. Practical issues, make sure when you build your sims, you'll see this come up, that if you use different time units, so you can specify that it'd be convenient to specify that your car wash is in seconds, but your inter-arrivals are in minutes. Well, that's fine, but you need to make sure you either explicitly tell Arena that 1 seconds and 1's minutes, or convert them all to a common unit, or else you'll get an issue with things arriving too fast or too slow. The other thing is if you're modeling very, very small activity durations, you can get round off error. And this isn't going to be an issue for like car washes, but if you're simulating like microprocessors, for example, then you might find that in reality, events can stack up much finer than your simulation can be, because they just arrive maybe smaller than the time scale that you can represent with numbers inside the simulation. And so that's something that generally you don't have to worry about in projects in this class, but you do have to worry about in real world systems if you're simulating high frequency events, high frequency trading, for example. So a lot of people use these things to simulate high frequency trading in accounting and in finance, and they have to be very careful about this round off error. Okay. Questions? Questions? Uh-huh.
Like multiply everything by a certain factor from the simulation, and then remove that factor. Is that still the same result?
So there's a question about how to handle round off error in a computer. There are a number of different ways to do it. I mean, if you can adjust the time scale of the system so you can spread things out, that can be one way, but a lot of times it's relative issues. It's sort of like, you might, in order to represent multiple ranges, so things that are spread very far apart, as well as things that are very tiny in the same sim, that kind of becomes the issue. So if you scale things up, then it might be that at this point, you now don't have a number that's big enough to represent these giant activity durations. So you might need a new numerical construct inside your programming language, something that's, not 64-bit behind the scenes, but 1,000 bits behind the scenes. And then it's a much more, maybe slower to handle that processing. Any other questions? Questions online? No, all right. All right, so as you're doing this homework, let's sort of step through the basic steps that you're going to be working with here. So the homework and the lab are both versions of a single server queue, where you've got a single channel that is generating arrivals and a single server that is processing them, and a queue that is allowing them to queue up. So we're going to kind of, now in this queuing network element is one that we can use to build lots of other different models. And so the rules that we're about to go for and how we manage the event calendar with this can be generalized to lots of other systems. And that's the reason why we're starting with this. So this is in some ways a simplistic system, but in other ways, this is a system that is usually a small component of most other very complicated or complex systems. All right, so whenever we're simulating a single channel queue like this one here, then our first step is to schedule the first arrival at time 0, the instant the simulation starts. We also typically, and this is what you'll do in your homework, schedule an end event to occur after a reasonable simulation interval. In reality, sometimes the end events are state dependent. So sometimes you want the simulation to run until there are no customers left. But in our case, for your first homework, I'm going to just tell you the simulation ends after 30 minutes. So you schedule a fictitious end event. It isn't an event that actually changes the state of the system. It changes the clock of the system. It doesn't change any of the state variables, but it just tells you our simulation's done. You can stop simulating now. And then you continuously process scheduled events in the appropriate order until you reach that end event. So this is the first thing you do. Schedule the first arrival at time 0. Then as you're iterating through your event calendar or your future event list, if you hit an arrival, then you move clock forward to that arrival time. So in the calendar, the arrival will be at time 5. So then you say clock is equal to 5. You move the clock to that time. And then you ask, is the server available up here? So is the service node here? Is this server available when at the instant of this arrival. If the server is not busy, if they're idle, then you move that arrived entity directly into the server. You draw a service time. I'll provide you a list of service times. In the future, we'll draw them randomly. So you draw a service time, and then once you know the service duration, that activity, you can then add to the event calendar a departure event that time in the future. So if this service takes 5 minutes, you schedule 5 minutes ahead of time, and then that's when you schedule this entity as getting out of that server. If instead the server is busy, then there is a state variable internally you'll have that will be the queue of entities waiting for that server, and you're going to just add them to that queue. And then at this point, whenever you schedule an arrival event, you have to schedule the next arrival event. So you're going to then draw from the inter-arrival times, either a random number or just take the number that I give you, the next arrival time, and you're going to schedule that as a future event to process a future arrival that will go through this logic. So you create that event, and then if there's any statistics you want to collect, like the number of arrivals or the maximum, how long the queue is, like you could say like, oh, well, now the maximum queue length is just increased, so I want to update that statistic, you do that here. Then you're done with your arrival event. So then you go to the event calendar and you look for the next event, which might be another arrival event. But in these systems, it'll probably be like a departure event. So if you happen to hit a departure event, as with all events, you move clock forward to that event time. If the wait queue is not empty, if someone's waiting, now the server is idle, and so you can move someone immediately into it. So you move the first entity from that queue into the server, draw a service time from the list or randomly, and then schedule a departure event for that one that you just moved into the server. So in this case, the server is idle just for a blink of an eye and immediately goes back to being busy. And then you update and collect statistics. And then finally, you'll hit the end event where you just move clock to that event time, update your statistics, and terminate your simulation. On your homework, you don't even have to create another separate line for the end event. You can just stop on the last line where the next event in the calendar is an end event. So you don't effectively, you just be copying down if you created a separate line for the end event. So you don't actually have to go forward here. But when you hit that end event, that basically means stop your simulation. Commonly used state variables are things like whether a server is busy or idle, how many entities are currently in the server, and which entities are those maybe, the number of entities currently waiting for the server, and potentially which entities are those. Common attributes that you might stamp on entities are their arrival time. That way, when they depart, you can keep track of how long they've been in the system. So in the next lecture, we'll actually walk through a hand simulation, a case where we'll do all of these to those numbers, very similar to the way you'll do in your homework. All right, so any questions about that, about these steps? I want to give you the steps so you can potentially try those ahead of time on that homework, and then we're going to walk through a simplified version of your homework example on Thursday. Okay. Questions online? All right. Okay, so the last couple of things I'll mention here. So after you run the simulation, there are a number of different ways we evaluate performance, and there can be a ton of these. These are just a couple of examples. So after a simulation runs, you could count the number of parts you've produced in a simulation. You could count, or you could keep track of what's the maximum waiting time that you experienced at across entities or at a particular queue. That's another, these are all things to evaluate how well the whole system is doing. So good systems produce lots of parts, good systems have low maximum waiting times. Average waiting time is an alternative to that. So across all of these parts, you could say, what is the average time a part took, either through the whole system or at a particular queue for this particular part, and then that sort of tells you that whether this queue is healthy or not. There are you can also average over time. And so you can say of a particular queue, look at how many entities are in the queue at every instant of time and take the integral of that, the area underneath that curve, and divide it by the total interval there. And that gives you the time average of how many entities are waiting in a queue. The maximum number, how many entities at any instant of time are waiting in a queue? What's the maximum number that through the simulation run, we're ever waiting in that queue? Average and maximum total time for parts in the system. So you look at the parts and you say, how long did it take you to get through the whole system? Across all the parts, what's the average? Across all the parts, what's the maximum? These are all just examples of things that you might use to measure the efficiency of these systems. And then utilization, I mentioned this one earlier too, whether servers are idle or busy, or this can also be fraction of capacity, what's the average utilization, and more. So this is not meant to be an exhaustive list, but this is just an example of things that after you run a simulation, you can say, did my simulation perform well? These might be some of the meters on which you measure these simulations. So what would you do with that? So as an example, here is some variable output from these simulations here. So what I've shown here are different output variables: total production, average waiting time in queue, average total time in system, time average number of parts in queue, and drill press utilization. So these are the performance variables are shown on the x-axis here. And there are circles, which are one system. So those are baseline arrival rate. And there are triangles, which are another system. That's when you double the arrival rate. And for both of these conditions, baseline arrival rate and doubled arrival rate, we ran 5 simulation replications. Every replication gave us a different output. So if we compared any two, so any, like the initial ones are black here. So the black circle to the black triangle, black circle to black triangle. If we ran one simulation run in this condition and one in this condition, then the blacks would be the ones we would be comparing. And that comparison may or may not be a general trend. We have to kind of look at all of these together. If we look at all of these together, we see that these circles variation overlap the triangle variation. So really, there's probably no difference in total production between these two. But if I look at like average total time in system, the average circle is sort of much lower than the average triangle, but not that much lower. So I have to use statistical methods to compare these variable outputs of these two different conditions. And that's kind of what we're going to be doing here. So high variability within treatments, need to use statistical analysis. And that's kind of the second half of the class is all about the right stats to use to analyze this type of variable data. All right, and that's all I've got for you today. Any questions about there? Actually, maybe let me just jump. I'll give you the other attendance question here, and then I'm happy to take questions after that. And I'll just type that back into the chat. And the second attendance question that I've got for today is, let's say, what are the inputs to a system, activities or delays? So the question there is, what are the inputs to the system, activities or delays? And there is a question in the chat. For any of you who have access permissions with that link, as we've mentioned before, you need to make sure you log in with your ASU account. A good trick you can do with that is to open up a new window, open up Google Drive, for example, open up your ASU account inside Google Drive, and then paste the link into that window. And after you've associated the link with your ASU account, then in the future, it should do that association automatically. All right. So with that, I'm happy to stick around for a couple other questions. Otherwise, that's all I got for you. So you feel free to go. Anything that I can help with. Don't forget ICA B2 due on Thursday. Homework's available. The next 2 homeworks are available. Lab 2 is available as well. All right. In that case, see you Thursday.